In this video, we describe the concepts and definitions that set up the mathematical properties of a worm-like chain. Our first definition is the contour length, L0, of a worm-like chain fiber, which is just the contour length as you trace along the fiber shown in black from one end to the other. The second definition is the end-to-end vector R, so that is just the vector from one end of the chain to the other end of the chain, which is shown here in red. Our third definition is the position S. So the position S is related to the contour length. It's the position along the contour of the fiber, but in this case it's an index into that fiber rather than the length. So it's just like we use X as an index into the length L of a beam. And so we're showing that here. Our next definition is the tangent vector, which is tangent to the fiber at S. So here we consider our initial position at the start of this has a tangent vector here that points off this way. But by the time we come along to this point, the tangent vector points off this way. And so the tangent vector is this T of S here that we show, but the last definition is this contour angle. Theta of S is the angle between the tangent vector at the start and at a position S along the fiber. We'll notice that we're particularly interested often in the contour angle theta of L0, that is the contour angle, the difference between the orientation of the start and end of the fiber. So note as we talk about these that R, the end-to-end length, T of S, the tangent vector at a position X, and theta of S, that angle between the initial tangent vector and the tangent at T of S, all depend on the conformation of the fiber. So if this fiber is undergoing thermal fluctuations, that is, like most molecules, wiggling around and changing shape all the time, that these things will constantly change over time. In contrast, S and L0 are properties, the distance along the contour length and the total contour length, that are independent of conformation. So we'll use these concepts now to describe the persistence length of a worm-like chain, which we refer to as L sub P, length and persistence, which is a really critical property of a nanoscale fiber. So consider now, as we brought up in the last slide, the idea of thermal fluctuations, that these conformations change constantly. So we can describe a time average conformation by asking what's the average cosine of that angle here that's between the initial and the tangent vector of S. We can ask about that time average cosine as it changes along the contour length. So when S is around 0, we're at the very beginning of the molecule, and so maybe we went from here to here. No matter how the conformation of this changes, because this doesn't have too tight a coil, we'll see that those tend to still be pointing in the same direction. So theta is around 0, and cosine theta of S remains around 1. That's for small s. But as S increases, the tangent vectors point in all sorts of different directions. So cosine of theta is decreasing with S until at large S, your theta of S will sample equally anything from 0 to 2 pi. That is, it can be pointing in any direction at all. So your tangent vector might be pointing equally likely in any direction independent of where the initial theta of 0 is. And so the average of this theta of S that now becomes the cosine theta of that is simply 0, because if the average of a cosine of a sinusoidal curve is 0, it has as much room above as below the point where it's 0, right? This is just the average of a sinusoid. So what we see then is that this cosine, turns out, we are not deriving the whole thing here, but it can be shown that that cosine theta f decays exponentially from 0 to 1. And so we would plot that and say, okay, here is this, and we have this exponential decay if we plot cosine theta of s against s. So if we look at that and say, well, where is it that we have e-fold decay? So this e-fold decay, we'll call that the persistence length. And so it's simply defined as that critical length for this exponential decay. So because the persistence length depends on how bendy this fiber is, how easily it bends, as we see in this picture, it's a property of the fiber structure. For example, actin filaments have a characteristic persistence length, microtubules do, DNA does. So this is what we mean by fiber structure. Now consider, if the contour length of a fiber is much shorter than the persistence length of that type of fiber, then it's like asking, what does a fiber this long act like? Well, it can't bend very much because it's at a length that's too short for how fast it bends. That is, it's in here much shorter than the persistence length. We're talking about L naught at this point. In that case, it's nearly straight. The cosine theta is close to 1, so we're saying S is really close to 0. So in this case, we have a straight fiber. If, on the other hand, the contour length and the persistence length are about the same, now we have L naught over here. So in this case, we've had a considerable drop, and so it may be pointing in a number of different directions. This is just one example of an orientation, but it might be pointing that way, that way. It'll be fluctuating between all of these things. And so it's a very flexible rod. So I think this is like rigid rod. This is a very flexible rod, but it's still what we think of as a rod. It's still kind of straight. Finally, if contour length is much greater than persistence length, then this thing acts like a string or a worm-like chain. It's all curled up in different orientations. In this way, we see that the persistence length LP determines the properties of a fiber. Now, we might ask, well, how is persistence length determined? So there's 3 main ways that this can be determined. One of it is that you can actually look at its conformations in a microscope if you fluorescently label a single fiber, maybe anchor one end or even leave it free, but photograph the conformations in a video over time. So you might see something kind of moving around like this over time. And if you consider all of those conformations, and for each of them you just calculate cosine theta of s, and then you can calculate the average cosine theta of s, and you can do this for a series of distances along each of those fibers. That is a series of values of s, and then when you plot that, you'll see an exponential decay. You'll fit the decay curve and calculate the persistence length. Another way to calculate the persistence length is to estimate it from theory. If you know the cross-sectional geometry, I, that is and the Young's modulus, E, that is, if you know the flexural rigidity of a fiber, you know something about how bendable it is. And it turns out that the persistence length depends on that flexural rigidity and on the temperature, because the requirement here is that the bending energy is less than thermal energy. So this can be expressed as this equation, that the persistence length is the flexural rigidity divided by kBt, where kb is the Boltzmann constant, which is just the R, the gas constant, divided by Avogadro's number. That is, the Boltzmann constant is a molecular rather than a molar version of the gas constant, which, if you recall, determines statistical mechanics of gases. And so this is just statistical mechanics of single molecules. So then thermal energy is just that times the temperature. And so that allows you to estimate if you know something about these properties. And this is often very useful when we look at proteins, because proteins tend to have a Young's modulus of around 2 gigapascals. We learned that on Friday when we talked about linear materials. And we can estimate I from anything like X-ray crystallography, not X-ray crystallography, but cryo-EM, which is a method of visualizing structures of nanoscale fibers and getting their geometry through electron density clouds. So the third way we can estimate the material properties of a fiber, or the persistence length of a worm-like chain, is that we can stretch a fiber under force. And when we stretch a fiber under force, we obtain a force extension curve. And we'll see in the next slide that you can estimate what the force extension curve should look like as a function of persistence length. So that also allows you to take an experimental measurement and fit the persistence length to it.